Imagine you fall toward a black hole, not metaphorically, actually. You're in a spacesuit, falling feet first toward a swirling dark heart of a collapsed star, and somewhere ahead of you is a boundary that every physics textbook on Earth calls the event horizon. The point of no return, the line where escape becomes mathematically impossible. Here is the unsettling part. According to the strict definition physicists have used for over 50 years, nobody, not you, not the most advanced telescope on Earth, not even a godlike observer with infinite computing power, can know exactly where that line is located right now. Not because the equipment isn't good enough, because the answer depends on something that hasn't happened yet. It depends on the entire future of the universe. That's not science fiction. That is the literal, mathematical definition of an event horizon, and it has been quietly bothering some of the most respected minds in theoretical physics for decades, including, in his final working years, Stephen Hawking himself. And here's where the story gets genuinely strange. A growing body of work in general relativity suggests that physicists may have had the causal order backwards the entire time. We were taught that a black hole forms, and as a consequence, an event horizon appears around it, a kind of cosmic do not enter sign that snaps into existence because the black hole is there. But some of the most careful mathematical work on this subject suggests something closer to the reverse. The thing physicists can actually detect, locate, and build their equations around, a boundary called a trapped surface, may come first. The event horizon, the one in every documentary, every textbook diagram, every popular explainer video, might not be the cause of the black hole's strangeness. It might be a kind of after-the-fact label, stitched on retroactively once the universe's entire future has already played out. If that sounds like a technicality, stay with this, because it isn't. It cuts to the heart of one of the strangest unsolved puzzles in modern physics, the black hole information paradox. And by the end of this video, you'll understand why some scientists now suspect that the point of no return we've all been picturing might not even be a real, physical thing happening at any single moment in time at all. Let's take this apart, piece by piece, because the real story is far stranger and far more satisfying than the simplified version everyone learned in school. To understand why this question matters, we need to go back to the basic picture most of us carry around in our heads, the one that comes from popular science shows, movies, and even most planetarium presentations. A massive star runs out of fuel. Gravity wins. The star collapses inward, crushing itself into an impossibly dense point. And as that happens, a boundary forms around it, a sphere of no return, beyond which the pull of gravity is so extreme that not even light can escape. That sphere is the event horizon. Cross it, and you're gone, forever. No signal, no light, no information of any kind can climb back out. This is the version of black holes that comes from Carl Schwarzschild's 1916 solution to Einstein's equations, found astonishingly fast. Just a few months after Einstein published general relativity itself, while Schwarzschild was serving on the German front lines in World War I. It's elegant, it's mathematically clean, and for most everyday purposes, it's a perfectly good way to think about black holes. But here is where things get interesting, and this is documented, mainstream, peer-reviewed physics, not speculation. The actual technical definition of an event horizon used by relativists is what's called teleological. That word comes from the Greek telos, meaning end or purpose. And in this context, it means something very specific and very strange. To know exactly where the event horizon is located today, you would need to know the entire future evolution of the universe, all the way to what physicists call future null infinity, essentially the infinitely distant future of space-time. Let that sink in for a second, because it's one of the strangest sentences in all of physics. The boundary that supposedly marks no escape right now, this instant, cannot actually be pinned down right now, this instant. Its exact location depends on events that haven't happened yet. If a star happens to fall into the black hole next Tuesday, the event horizon was technically already slightly larger today before that star ever fell in, because the horizon's location is defined by what eventually becomes trapped, looking backward from the end of time. This is not a fringe idea or a contrarian take from one eccentric physicist. It's built directly into the formal mathematics of general relativity, and it creates a genuinely uncomfortable problem for anyone trying to do real physics with black holes, especially the people who run computer simulations of colliding black holes to predict the gravitational waves that detectors like LIGO actually observe. Here's the practical problem this teleological weirdness creates, and it's the kind of problem most people watching black hole content never even hear about. If you're a physicist trying to simulate two black holes spiraling into each other, an event that LIGO has now detected directly dozens of times since 2015, you cannot, even in principle, use the textbook event horizon while the simulation is actually running. Why? Because the simulation hasn't reached the future yet. The computer doesn't know what's going to happen next, by definition, since that's literally what it's calculating. Asking it to locate the true event horizon during the merger is like asking someone to tell you their final score in a video game while they're still only halfway through level 1. So physicists needed something else, something local, something you could actually compute using only the information available right now in the present slice of space-time without needing to peek into the future. That something is called a trapped surface, and is the real protagonist of this story. Here's the intuitive version. Imagine a sphere of light rays, like a flashbulb, going off, expanding outward in all directions from some point in empty space. Normally, both the rays heading outward and the rays heading inward behave the way you'd expect. The outward ones spread apart and get bigger. The inward ones converge and get smaller. That's ordinary, flat, boring space-time. But inside a black hole, something genuinely bizarre happens to that picture. Gravity becomes so overwhelming that even the outward traveling light rays, the ones trying to expand away from the center, start shrinking instead. Both the inward and outward light rays converge. Space itself has become so warped that there's no version of outward left that actually leads outward. This region, where light moving in every direction is being squeezed inward by gravity, is what physicists call a trapped surface. And here's the crucial difference from the event horizon. You can find a trapped surface using only local information about the geometry of space-time right now, today, in this instant, without knowing anything about the future. No teleology required. It's not a label that gets applied retroactively after the universe finishes playing out. It's something a physicist, or a sufficiently advanced computer simulation, can actually point to and say, with confidence, there it is, right now. The boundary of the region, containing all of these trapped surfaces, is called an apparent horizon. And this is where our story takes its central turn. For decades, the relationship between apparent horizons and the real teleological event horizon was treated mostly as a technical footnote, useful for numerical relativists running simulations, but not something that changed the fundamental story for everyone else. The assumption was simple. A black hole forms. The true event horizon exists out there as the real boundary, and the apparent horizon is just a convenient, locally computable stand-in that usually sits close to where the real horizon should be. But a body of theoretical work, including results connected to Douglas Earley's conjecture from the 1990s, and later proven in specific cases by researchers like Ben Dove, suggested something more provocative, that under many physically reasonable conditions, the event horizon can actually be reconstructed from the boundary of trapped surfaces, rather than the other way around. In other words, the locally detectable, non-teleological apparent horizon isn't just a stand-in for the real thing. It may be doing the actual physical work. The globally defined, future-dependent event horizon may simply be the mathematical shadow that this local structure casts forward across the rest of space-time's history. This is a genuinely significant reordering of cause and effect. The popular story says, black hole forms, therefore event horizon appears, marking its boundary. The more careful mathematical story says something closer to trapped surfaces form, locally, causally, right here and right now, as a direct physical consequence of gravitational collapse. And the event horizon is the global, retrospective pattern that emerges from connecting all of those local trapped regions across the entire future history of space-time. The wall most people picture isn't the cause of the black hole's strangeness. It's closer to a kind of after-the-fact bookkeeping device, useful for certain theoretical purposes, but not the physically fundamental thing happening to matter as it falls in. Now, here's where this stopped being a quiet technical curiosity among relativists and started becoming something that even Stephen Hawking, arguably the most famous black hole physicist in history, felt compelled to address publicly, in his own words, on the record. In a 2014 paper, and in subsequent public talks, Hawking made a statement that generated significant media confusion at the time, with some outlets sensationally and inaccurately reporting that he claimed black holes don't exist. That is not what he said. What he actually proposed, in careful technical language, was that the absence of true event horizons in the strict teleological sense means there are no black holes in the specific sense of regions from which light can never, under any circumstances, escape to infinity. He argued instead that what actually forms are apparent horizons, which can persist for long periods of time, behaving for all practical purposes exactly like the black holes we're used to, trapping light and matter for the very long duration that they exist, but without carrying the absolute, eternal, teleological guarantee built into the classical event horizon picture. Why would one of the most celebrated physicists in modern history spend his final working years drawing such a fine distinction? Because of a problem that had been gnawing at theoretical physics since the 1970s, one that Hawking himself had originally helped create, the black hole information paradox. Here's the paradox, and it's worth slowing down for, because it's one of the most genuinely mind-bending unsolved problems in physics. The kind of thing that sounds like a logic puzzle, but is actually a real crisis at the foundation of how we understand reality. Quantum mechanics insists, as one of its most sacred and well-tested principles, that information cannot simply vanish from the universe. If you burn a book, the information about every word on every page isn't truly destroyed. It's scrambled into smoke, heat, and ash in a way that is, in principle, if you had impossibly precise instruments, fully reconstructible. The universe keeps its receipts, always. But the classical event horizon, the eternal, absolute, one-way membrane of general relativity makes a very different promise. Once something crosses it, it's gone. Not scrambled. Not hidden. Genuinely, permanently inaccessible to the rest of the universe, forever, as a matter of fundamental geometry. Hawking himself discovered in the 1970s that black holes slowly radiate energy away, a process now called Hawking radiation, and that this radiation appears to be purely random, thermal noise, carrying no information whatsoever about what fell in. So picture the conflict. You drop your physics textbook into a black hole. According to quantum mechanics, the information describing every atom of that book must, in principle, still exist somewhere in the universe, even if scrambled beyond any practical recognition. But according to the classical picture of an eternal event horizon combined with purely random Hawking radiation, that information has crossed a boundary from which nothing returns. And what comes back out is structureless noise. Something has to give. Either quantum mechanics is wrong about information being conserved, which would be one of the most catastrophic results in the history of physics, or general relativity's classical picture of an absolute. Eternal event horizon isn't quite the full, fundamental story. This single contradiction has occupied some of the sharpest minds in theoretical physics for half a century, and it remains, even now, formally unresolved at the deepest level, though there has been genuine, significant progress, including breakthrough work in the last several years, using mathematical objects called islands and replica wormholes that suggest information may, after all, gradually leak out of black holes encoded within the Hawking radiation itself, a result that earned widespread acclaim in the theoretical physics community. Now here's where our earlier discovery about trapped surfaces versus event horizons reconnects directly with the information paradox, and this is the part that should genuinely surprise you. If the real physical boundary that matter experiences while falling into a black hole is the locally defined, causally determined, apparent horizon, rather than the globally defined, teleological event horizon, then the absolute, eternal, nothing ever escapes guarantee starts to look less like a fundamental law of nature and more like an idealized mathematical limit, one that real, physical, evaporating black holes might never actually achieve in finite time. Remember, Hawking's own calculations showed that black holes slowly evaporate, losing mass through Hawking radiation, shrinking over unimaginably long timescales until, eventually, they're gone entirely. If a black hole eventually evaporates completely rather than persisting forever, then, strictly speaking, by the teleological definition, a true event horizon might never have formed in the first place, because the future history required to define it never includes an eternal black hole at all. The apparent horizon, the local trapped region that genuinely forms during collapse, does the real physical work of trapping light and matter for a very long but ultimately finite time. The event horizon, meanwhile, becomes something closer to a convenient approximation, useful for many calculations, accurate to extraordinary precision for the lifetime of the black hole, but not the eternal, fundamental, information-destroying wall that the popular imagination and frankly generations of physics textbooks had assumed it to be. This matters enormously for the information paradox, because if there's no truly eternal, absolute one-way membrane, just a long-lived but ultimately temporary trapped region, the philosophical pressure pushing physicists toward information is destroyed forever weakens considerably. The information doesn't need to escape through an impossible, paradox-generating wall. It may simply be encoded in extraordinarily scrambled form in the radiation that gradually leaks out as the apparent horizon, not some eternal event horizon, slowly shrinks and eventually disappears. Let's pause and build a clear mental model of what's actually being proposed here, because it's easy to lose the thread in the technical vocabulary. Picture a calm lake. Drop a heavy stone into it, and ripples form, a real, physical, observable, local event happening right at the moment of impact. That's roughly analogous to a trapped surface. Real, local, happening now, detectable, using only information available at this instant. Now imagine trying to draw, on a single static map, the complete pattern of every ripple that will ever exist on that lake, including ripples from stones that haven't been thrown yet, accounting for exactly how each ripple interacts with every other ripple for the rest of eternity. That impossibly complete, all future inclusive map is roughly analogous to the teleological event horizon. It's a real mathematical object you could, in principle, construct if you somehow already knew the lake's entire future. But it's not the thing actually causing the water to move. The local splash is doing that. The map is just an extremely thorough after-the-fact record of where all the splashes ended up mattering. This is, of course, a simplified analogy, and like all analogies about black holes, it shouldn't be pushed too literally. Space-time curvature is a far stranger beast than ripples on water. But it captures the essential reordering this video has been building toward. The local, causal, happening right now structure may be the physically fundamental thing. The global, teleological event horizon may be the derived, retrospective bookkeeping device, not the cause of a black hole's strange, light-trapping behavior, but a particular, idealized mathematical summary of it. At this point, it's worth being completely honest about where the genuine scientific uncertainty actually lies, because this is not a settled, unanimous matter in physics, and presenting it as one would be misleading. First, this entire conversation about apparent horizons versus event horizons takes place within classical general relativity and semi-classical approximations that combine general relativity with some quantum effects. Nobody has a complete working theory of quantum gravity, the framework that would actually describe what happens to space-time itself at the smallest scales near a singularity. Until physicists have that complete theory, every statement about what's really happening at a black hole's boundary carries an asterisk. This is our best current mathematical framework, not a final, experimentally confirmed answer about ultimate physical reality. Second, not all physicists agree on how seriously to take the distinction between apparent and event horizons as physically meaningful versus merely a useful calculational tool. Some researchers argue that for astrophysical black holes, the ones actually out there in space, formed from collapsing stars, merging in events LIGO detects, the difference between the apparent horizon and the idealized event horizon is so fantastically small, often differing only in how a black hole's final, almost imperceptibly distant evaporation in the far future is accounted for, that it has essentially zero practical consequence for understanding what we actually observe. They'd argue this is an important technical refinement for mathematical rigor and for resolving deep paradoxes, but not a revolution that overturns how black holes behave in any way that changes astronomy as practiced day to day. Third, and this is the genuinely contested frontier, the question of exactly how information escapes, whether through the islands and replica wormhole calculations mentioned earlier, through some other yet undiscovered mechanism, or through some combination of effects nobody has fully worked out yet, remains an active, unresolved area of research, not a closed case. The recent island and replica wormhole results are genuinely exciting and represent real progress, earning significant attention precisely because they suggest, for specific simplified model black holes, that information can indeed be recovered, consistent with quantum mechanics. But translating these results fully and rigorously to realistic, four-dimensional, astrophysical black holes remains a significant, ongoing challenge that theoretical physicists are still actively working through. So the honest summary is this: there is a real, mathematically serious case built on solid technical foundations going back decades and championed in different forms by figures including Hawking himself in his later years, that the causal story of black holes runs differently than the popular picture suggests, with local trapped surfaces doing the real physical work and the global event horizon serving as a kind of idealized, after-the-fact summary. But this remains an actively developing area of theoretical physics, not a fully settled textbook fact that has replaced the old picture everywhere. So what does any of this actually change, beyond satisfying a craving for mind-bending trivia? Here are the genuine, documented implications, ranging from the highly practical to the deeply philosophical. On the practical side, this reframing is precisely why every gravitational wave detection made by LIGO and Virgo since 2015 relies on numerical relativity simulations that track apparent horizons, not teleological event horizons, while modeling colliding black holes. The entire, remarkably successful field of gravitational wave astronomy, the one that has now confirmed dozens of black hole mergers and earned a Nobel Prize in 2017, is built on quietly treating the locally computable apparent horizon as the physically relevant boundary during a merger, precisely because the teleological event horizon is computationally useless while a simulation is actually running. In other words, this isn't an abstract philosophical curiosity sitting in some ivory tower. It's the working, load-bearing foundation underneath one of the most successful experimental triumphs in 21st century physics. On the philosophical side, it reshapes how we should think about the famous phrase, point of no return. If the true fundamental physics is about a local, causally well-defined trapped region rather than an eternal teleological wall, then black holes may be less like cosmic prisons with permanently locked doors, and more like extraordinarily long-lived, temporary traps, regions where escape is, for all practical purposes across timescales vastly longer than the age of the universe, essentially impossible, but not absolutely, eternally, mathematically impossible in the strict, infinite sense the word horizon originally implied. And on the information paradox itself, this reframing offers something genuinely valuable, a path by which the universe's books can still balance. Information isn't destroyed by crossing some impossible, paradox-generating eternal wall. It's scrambled, encoded, and eventually, across an almost unimaginably long time, returned to the wider universe as the black hole's temporary trapped region gradually, slowly, but not eternally, gives way. There's one more thread worth pulling before we close, because it connects this entire investigation back to something timeless about how science actually progresses, not in dramatic, single-paper revolutions, but in slow, careful re-examinations of definitions that everyone assumed were already settled. For most of the 20th century, event horizon functioned as a kind of unquestioned bedrock term, a settled piece of vocabulary baked into how physicists talked about black holes, the way atom once meant an indivisible particle before physicists discovered protons, neutrons, and electrons hiding inside. The teleological event horizon was mathematically valid, rigorously derived, and genuinely useful for many purposes. It simply wasn't, on its own, the whole physical story. This is a pattern that shows up again and again across the history of physics. A concept that works brilliantly as an approximation gets gradually revealed to be standing on top of a deeper, more local, more physically grounded structure. Temperature works as a useful concept long before anyone understood it as the statistical motion of countless individual molecules. Pressure works as a useful concept long before the kinetic theory of gases explained what was actually happening underneath. In each case, the older concept didn't get thrown away. It got recontextualized, understood as an emergent, often extremely accurate, but ultimately derived description of something more fundamental happening underneath. The event horizon may be undergoing exactly this kind of transition right now, in real time, within the careers of physicists working today, not discarded, not proven wrong in any dramatic sense. Simply recontextualized, understood now as the global idealized shadow cast by something more immediate, more local, and more physically real. The trapped surface forming right now, right here, the moment gravity wins. So here is where this investigation leaves us, and it's worth sitting with the strangeness of it rather than rushing past it. We grew up with a simple, vivid picture. A black hole forms, and around it snaps into existence an absolute, eternal boundary called the event horizon, the point of no return, the cosmic line in the sand. It turns out that boundary, the one in literally every documentary, including quite possibly several you've watched on this very platform, may not be the cause of a black hole's strangeness at all. It may be the long shadow that strangeness casts forward across the rest of time, calculated only after the fact by an observer who would need to already know how the entire universe turns out. What's actually happening right now to anything falling toward a black hole is something more immediate, more local, and in a strange way, more honest. A trapped surface, a place where every direction has quietly stopped being outward, forming in this instant, with no need to consult the future at all. So here's the question worth sitting with, the one this video leaves you to turn over in the comments. If the boundary we've been calling the point of no return turns out to be less like a wall and more like a long shadow cast by something else entirely, what other obvious textbook facts about the universe might also turn out to be standing on foundations nobody has properly questioned yet, simply because the old picture has worked well enough, for long enough, that nobody thought to ask what was really happening underneath?